The purpose of this video is not to explain why the formulas and operations are what they are, but to try to explain the intuitions behind what they do. We'll analyze a case hopefully easier to understand than a classical Kalman filter, but a case nonetheless exhibiting very similar behavior. Most of the material in this video aligns with the contents of the excellent book Kalman and Bayesian Filters in Python by Roger R. Loud Jr. Let's begin. Imagine a circular tunnel connecting 10 rooms numbered from 1 to 10. In one of the rooms there is a robot and we only know approximately where the robot is. Let's assume the probability distribution is discrete. The robot is most likely in room 5. Let's assume that the robot moves in discrete steps from left to right. How will the probability distribution look like after one move? We definitely know that the robot moved, so the probability shift from left to right by one room. Now let's think about this operation in terms of combining probability distributions. The information that the robot moves from left to right, one room at a time, can be described by following probability distribution. This means that the robot will definitely move by one room to the right at each step. Now it's easy to see what mathematical operation can be used to achieve our desired shifting of the probabilities in the probability distribution. We must slide the robot's movement probability distribution across each probability of the position distribution, multiplying and adding probabilities. The movement probabilities need to be used in reversed order. You can think of it as interpreting the probability distribution in the following way. At current step, what is the probability we've moved from the current position, i.e. we stayed in the same position, and what is the probability we've moved from the left position? Symbolically, the operations are. Now we can generalize to a single formula. This operation is what in mathematics is called convolution, and in probability theory corresponds to the addition of independent random variables. This is also called total probability theorem, or the law of total probability. Written somewhat informally, like this, it can be viewed as an instance of Chapman-Kolmogorov equation, which actually is just a marginalization over the nuisance variable. The range of x in our case would be from n-1 to n. We won't go deeper into this here. All those terms can be a good anchor points to more research. Expressing the operations as combining probability distributions allows us to model more realistic cases. Like this one, where we assume that there is 1 in 5 chance that the robot will glitch and stay at the same position. Convolution is like a weighted average, so that is why the probability distribution gets sort of smeared or stretched after a prediction step. The mode of the distribution, so the maximum probability also gets smaller. This shows us that the prediction step is inherently a lossy operation. This might also remind you of low-pass filtering. Next, we'll see what are the effects of making multiple successive predictions. We assume the same initial position probability distribution as before, and the movement probability distribution corresponding to reliable movement in the right direction. The individual probabilities shift to the right. No surprises here. We don't know exactly where the robot is due to the small probability for most of the rooms, but at least our predictions don't introduce additional uncertainty. Even after 56 updates, there is no loss of information. Now let's analyze a more interesting and more realistic case. We assume the same initial position probability distribution, but the robot moves to the left with probability 0.9 now, and there is a 0.1 probability of a slip, or a glitch which results in the robot staying in the same room. After first prediction, there is not much loss of certainty. Successive predictions, however, show that we're slowly losing the track of the robot's position. After 56 updates, the probability distribution became almost flat. Final case we'll analyze is as follows. Now the glitch can happen in both directions. The robot can stay in the same place, but also can slip and move 2 rooms to the right. The situation is even worse than before. We're losing track of the robot position even faster. This losing of information will always be happening with uncertain predictions or noisy model of the system. The only way to overcome this is to incorporate additional information from measurements. Next, we'll try to show exactly that. Let's assume we don't know where the robot is, so each room is equally likely. The position probability distribution looks like this. It turns out each room has one of 2 colors, red or blue. The robot has a sensor capable of reporting the room wall's color. For example, if the robot reports color red, the probability distribution gets updated like this. We see that this radically improved things. We rejected most of the tunnel positions and increased our belief in the remaining positions, in this case, by a factor of 3. In real world, however, the sensors are not perfect and the measurement almost always is noisy. Let's go back to our initial uniform distribution. Now what will happen with the noisy sensor, a sensor that is 3 times more likely to be right than wrong? We can see now that the probabilities of color red versus color blue is 3 times larger, and the probabilities of color blue are greater than 0. What is the mathematical operation we use to update the position probability distribution? We multiply element-wise our position probability distribution, our prior knowledge, with a vector of weights expressing the likelihood of new knowledge provided by our sensor. Multiplying probability distributions this way, or the more a likelihood, which is not a probability distribution, doesn't guarantee that we'll get a probability distribution back, so a normalization is also needed. In short, this is which is a version of Bayes' theorem, often seen in literature in this form where the denominator corresponds to the normalization. We won't get deeper into this here. We just need to know that Bayes' theorem allows us to incorporate new knowledge into our prior knowledge. We now know how to combine uncertain predictions with uncertain measurements. Let's see what happens after more alternating prediction and update states with uncertain predictions and updates. The gray circle represents the robot. The movement uncertainty is 1 in 10. It seems that we can track the robot just fine. Let's run some more updates. We can see that on the long stretch of blue rooms we're losing information, but the less frequent red rooms make up for this. There is less red rooms, so the update for them contributes more to the increase of our confidence. Let's now see what happens if the robot glitches once in a while. The system can resynchronize and the robot's position is tracked correctly. We now have basic knowledge of how to handle unreliable information to make best estimates. The principles explained in this video are exactly the same as in case of a classical Kalman filter. It also operates in 2 steps: predict and update. The differences are more quantitative than qualitative. The classical Kalman filter operates on multidimensional and continuous, normal, so on model distributions. And the last difference is that the measurements are indirect. We'll unpack what it all means in the next videos. That's it for this video. I hope it was at least somewhat helpful. Thank you.